A sailplane or glider is a type of glider aircraft used in the sport of gliding. Sailplanes are aerodynamically streamlined and are capable of soaring in rising air. Types of gliders. Sailplanes benefit from producing the least drag for any given amount of lift, and this is best achieved with long, thin wings, a fully faired narrow cockpit and a slender fuselage. Aircraft with these features are able to climb efficiently in rising air produced by thermals or hills. Sailplanes can glide long distances at high speed with a minimum loss of height in between. Gliders have rigid wings and either skids or undercarriage. In contrast, hang gliders and paragliders use the pilot's feet for the start of the launch and for the landing. These latter types are described in separate articles, though their differences from sailplanes are covered below. Gliders are usually launched by winch or aero tow, though other methods, auto tow and bungee, are occasionally used. All sailplanes soar, but some gliders do not soar and are simply engineless aircraft towed by another aircraft to a desired destination and then cast off for landing. Military gliders are single-use only, and are abandoned after landing, having served their purpose. Motor gliders are gliders with engines which can be used for extending a flight and even, in some cases, for takeoff. Some high-performance motor gliders may have an engine-driven retractable propeller which can be used to sustain flight. Other motor gliders have enough thrust to launch themselves before the engine is retracted and are known as self-launching gliders. Another type is the self-launching touring motor glider, where the pilot can switch the engine on and off in flight without retracting their propellers. History. Sir George Cayley's gliders achieved brief wing-borne hops from around 1849. In the 1890s, Otto Lilienthal built gliders using weight shift for control. In the early 1900s, the Wright brothers built gliders using movable surfaces for control. In 1903 they successfully added an engine. After World War I, gliders were built for sporting purposes in Germany and in the United States. Germany's strong links to gliding were to a large degree due to post-WWI regulations forbidding the construction and flight of motorized planes in Germany, so the country's aircraft enthusiasts often turned to gliders and were actively encouraged by the German government, particularly at flying sites suited to gliding flight like the Wasser Cup. The sporting use of gliders rapidly evolved in the 1930s and is now their main application. As their performance improved, gliders began to be used for cross-country flying and now regularly fly hundreds or even thousands of kilometers in a day if the weather is suitable. In 1930, pilot Frank Hawks flew the Texaco Eaglet with tow plane from San Diego to New York over 8 days, helping to popularize the activity in the United States. Glider design. Early gliders had no cockpit and the pilot sat on a small seat located just ahead of the wing. These were known as primary gliders, and they were usually launched from the tops of hills, though they are also capable of short hops across the ground while being towed behind a vehicle. To enable gliders to soar more effectively than primary gliders, the designs minimized drag. Gliders now have very smooth, narrow fuselages and very long, narrow wings with a high aspect ratio and winglets. The early gliders were made mainly of wood with metal fastenings, stays and control cables. Later fuselages made of fabric-covered steel tube were married to wood and fabric wings for lightness and strength. New materials such as carbon fiber, fiberglass and Kevlar have since been used with computer-aided design to increase performance. The first glider to use glass fiber extensively was the Akaflieg Stuttgart FS-24 Fair Paragraph Nix, which first flew in 1957. This material is still used because of its high strength-to-weight ratio and its ability to give a smooth exterior finish to reduce drag. Drag has also been minimized by more aerodynamic shapes and retractable undercarriages. Flaps are fitted to the trailing edges of the wings on some gliders to minimize the drag from the tailplane at all speeds. With each generation of materials and with the improvements in aerodynamics, the performance of gliders has increased. One measure of performance is the glide ratio. A ratio of 30:1 means that in smooth air a glider can travel forward 30 meters while losing only 1 meter of altitude. Comparing some typical gliders that might be found in the fleet of a gliding club, the Grun or Baby from the 1930s had a glide ratio of just 17:1, The glass fiber libel of the 1960s increased that to 39.1, and modern flapped 18-meter gliders such as the ASG-29 have a glide ratio of over 51. The largest open-class glider, the Eta, has a span of 30.9 meters and has a glide ratio over 70:1. Compare this to the infamous Gimli glider, a Boeing 767 which ran out of fuel mid-flight and was found to have a glide ratio of only 12:1, or to the Space Shuttle with a glide ratio of 4.5:1. Due to the critical role that aerodynamic efficiency plays in the performance of a glider, gliders often have aerodynamic features seldom found in other aircraft. The wings of a modern racing glider have a specially designed low-drag laminar flow airfoil. After the wings' surfaces have been shaped by a mold to great accuracy, they are then highly polished. Vertical winglets at the ends of the wings are computer-designed to decrease drag and improve handling performance. Special aerodynamic seals are used at the ailerons, rudder and elevator to prevent the flow of air through control surface gaps. Turbulator devices in the form of a zigzag tape or multiple blowholes positioned in a span-wise line along the wing are used to trip laminar flow air into turbulent flow at a desired location on the wing. This flow control prevents the formation of laminar flow bubbles and ensures the absolute minimum drag. Bug wipers may be installed to wipe the wings while in flight and remove insects that are disturbing the smooth flow of air over the wing. Modern competition gliders carry jettisonable water ballast. The extra weight provided by the water ballast is advantageous if the lift is likely to be strong, and may also be used to adjust the glider's center of mass. Moving the center of mass toward the rear by carrying water in the vertical stabilizer reduces the required downforce from the horizontal stabilizer and the resultant drag from that downforce. Although heavier gliders have a slight disadvantage when climbing in rising air, they achieve a higher speed at any given glide angle. This is an advantage in strong conditions when the gliders spend only a small amount of time climbing in thermals. The pilot can jettison the water ballast before it becomes a disadvantage in weaker thermal conditions. Another use of water ballast is to dampen air turbulence such as might be encountered during ridge soaring. To avoid undue stress on the airframe, gliders must jettison any water ballast before landing. Most gliders are built in Europe and are designed to EASA certification specification CS22. These define minimum standards for safety in a wide range of characteristics such as controllability and strength. For example, gliders must have design features to minimize the possibility of incorrect assembly. Automatic connection of the controls during rigging is the common method of achieving this. Launch and flight. The two most common methods of launching sailplanes are by aerotow and by winch. When aerotowed, the glider is towed behind a powered aircraft using a rope about 60 meters long. The glider pilot releases the rope after reaching the desired altitude. However, the rope can be released by the tow plane also in case of emergency. Winch launching uses a powerful stationary engine located on the ground at the far end of the launch area. The glider is attached to one end of 800 euro 1200 meters of cable and the winch rapidly winds it in. The glider can gain about 900 euro 3000 feet of height with a winch launch, depending on the headwind. Less often, automobiles are used to pull gliders into the air, by pulling them directly or through the use of a reverse pulley in a similar manner to the winch launch. Elastic ropes are occasionally used at some sites to launch gliders from slopes, if there is sufficient wind blowing up the hill. Bungee launching was the predominant method of launching early gliders. Some modern sailplanes can self-launch with the use of retractable engines and/or propellers, which can also be used to sustain flight once airborne. Once launched, sailplanes try to gain height using thermals, ridge lift, lee waves or convergent zones and can remain airborne for hours. This is known as soaring. By finding lifts efficiently often, experienced pilots fly cross-country, often on pre-declared tasks of hundreds of kilometers, usually back to the original launch site. Cross-country flying and aerobatics are the two forms of competitive gliding. For information about the forces in gliding flight, see lift-to-drag ratio. Glide slope control. Pilots need some form of control over the glide slope to land the glider. In powered aircraft, this is done by reducing engine thrust. In gliders, Other methods are used to either reduce the lift generated by the wing, increase the drag of the entire glider, or both. Glide slope is the distance traveled for each unit of height lost. In a steady wings level glide with no wind, glide slope is the same as the lift-drag ratio of the glider, called L/D. Reducing lift from the wings and/or increasing drag will reduce the LD, allowing the glider to descend at a steeper angle with no increase in airspeed. Simply pointing the nose downwards only converts altitude into a higher airspeed with a minimal initial reduction in total energy. Gliders, because of their long low wings, create a high ground effect which can significantly increase the glide angle and make it difficult to bring the glider to Earth in a short distance. Side air slipping. A slip is performed by crossing the controls so that the glider is no longer flying aligned with the airflow. This will present one side of the fuselage to the airflow, significantly increased drag. Early gliders primarily used slipping for glide slope control. Spoilers. Spoilers are movable control surfaces in the top of the wing, usually located mid-chord or near the spar, which are raised into the airflow to eliminate the lift from the wing area behind the spoiler, disrupting the spanwise distribution of lift and increasing lift-induced drag. Spoilers significantly increase drag. Air brakes. Air brakes, also known as dive brakes, are devices whose primary purpose is to increase drag. On gliders, the spoilers act as air brakes. They are positioned on top of the wing and below the wing also. When slightly opened, the upper brakes will spoil the lift, but when fully opened will present a large surface and so can provide significant drag. Some gliders have terminal velocity dive brakes, which provide enough drag to keep its speed below maximum permitted speed, even if the glider were pointing straight down. This capability is considered a safer way to descend without instruments through cloud, than the only alternative, an intentional spin. Flaps. Flaps are movable surfaces on the trailing edge of the wing. The primary purpose of flaps is to change the camber of the wing and so change the lift-to-drag ratio of the wing. This reduces the stall speed and so allows reduced landing speeds. It was possible to lower the flaps on some older gliders by up to 90 degrees to increase drag significantly, as well as increasing lift coefficient when landing. Another feature that flapped gliders possess are negative flaps that are also able to deflect the trailing edge upward. This feature is included on some competition sailplanes in order to reduce the pitching moment on the wing and allowing better glide ratios at higher speeds. Parachute. Some high-performance gliders from the 1960s and 1970s were designed to carry a small drogue parachute because their air brakes were not particularly effective. This was stored in the tail cone of the glider during flight. When deployed, a parachute causes a large increase in drag, but has a significant disadvantage over the other methods of controlling the glide slope. This is because a parachute does not allow the pilot to finely adjust the glide slope. Consequently, a pilot may have to jettison the parachute entirely, if the glider is not going to reach the desired landing area. Landing. Early glider designs use skids for landing, but modern types generally land on wheels. Some of the earliest gliders used a dolly with wheels for taking off, and the dolly was jettisoned as the glider left the ground, leaving just the skid for landing. A glider may be designed so the center of gravity is behind the main wheel so the glider sits nose high on the ground. Other designs may have the CG forward of the main wheel so the nose rests on a nose wheel or skid when stopped. Skids are now mainly used only on training gliders such as the Schweizer SGS-2 Euro 33. Skids are around 100 mm wide by 900 mm long and run from the nose to the main wheel. Skids help with braking after landing by allowing the pilot to put forward pressure on the control stick, thus creating friction between the skid and the ground. The wingtips also have small skids or wheels to protect the wingtips from ground contact. In most high-performance gliders, the undercarriage can be raised to reduce drag in flight and lowered for landing. Wheel brakes are provided to allow stopping once on the ground. These may be engaged by fully extending the spoiler's air brakes or by using a separate control. Although there is only a single main wheel, the glider's wing can be kept level by using the flight controls until it is almost stationary. Pilots usually land back at the airfield from which they took off, but a landing is possible in any flat field about 250 meters long. Ideally, Should circumstances permit, a glider would fly a standard pattern, or circuit, in preparation for landing, typically starting at a height of 300 meters. Glide slope control devices are then used to adjust the height to assure landing at the desired point. The ideal landing pattern positions the glider on final approach so that a deployment of 60% of the spoiler's dive brakes flaps brings it to the desired touchdown point. In this way the pilot has the option of opening or closing the spoiler's air brakes to extend or steepen the descent to reach the touchdown point. This gives the pilot wide safety margins should unexpected events occur. Instrumentation and other technical aids. In addition to an altimeter, compass, and an airspeed indicator, gliders are often equipped with a variometer, turn and bank indicator and an airband radio, each of which may be required in some countries. An emergency position indicating radio beacon may also be fitted into the glider to reduce search and rescue time in case of an accident. Much more than in other types of aviation, glider pilots depend on the variometer, which is a very sensitive vertical speed indicator, to measure the climb or sink rate of the plane. This enables the pilot to detect minute changes caused when the glider enters rising or sinking air masses. Both mechanical and electronic varios are usually fitted to a glider. The electronic variometers produce a modulated sound of varying amplitude and frequency depending on the strength of the lift or sink, so that the pilot can concentrate on centering a thermal, watching for other traffic, on navigation, and weather conditions. Rising air is announced to the pilot as a rising tone, with increasing pitch as the lift increases. Conversely, descending air is announced with a lowering tone, which advises the pilot to escape the sink area as soon as possible. Gliders' variometers are sometimes fitted with mechanical devices such as a McCready ring to indicate the optimal speed to fly for given conditions. These devices are based on the mathematical theory attributed to Paul McCready, though it was first described by Wolfgang Spark-Currency-TE in 1938. McCready theory solves the problem of how fast a pilot should cruise between thermals, given both the average lift the pilot expects in the next thermal climb, as well as the amount of lift or sink he encounters in cruise mode. Electronic variometers make the same calculations automatically, after allowing for factors such as the glider's theoretical performance, water ballast, headwinds, tailwinds and insects on the leading edges of the wings. Soaring flight computers, often used in combination with PDAs running specialized soaring software, have been designed for use in gliders. Using GPS technology in conjunction with a barometric device, these tools can provide the glider's position in 3 dimensions by a moving map display, alert the pilot to nearby airspace restrictions, indicate position along track and remaining distance and course direction, show airports within theoretical gliding distance, determine wind direction and speed at current altitude, show historical lift information, create a GPS log of the flight to provide proof for contests and gliding badges, provide final glide information. Indicate the best speed to fly under current conditions. After the flight, the GPS data may be replayed on computer software for analysis and to follow the trace of one or more gliders against a backdrop of a map, an aerial photograph or the airspace. Because collision with other gliders is a risk, the anti-collision device FLARM is becoming increasingly common in Europe and Australia. In the longer term, gliders may eventually be required in some European countries to fit transponders once devices with low power requirements become available. Markings, so that ground-based observers may identify gliders in flight or in gliding competition. Registration marks are displayed in large characters on the underside of a single wing, and also on the fin and rudder. Registration marks are assigned by gliding associations such as the U.S. Soaring Society of America, and are unrelated to national registrations issued by entities such as the U.S. Federal Aviation Administration. This need for visual ID has somewhat been supplanted by GPS position recording. Insignias are useful in 2 ways. First, they are used in radio communications between gliders, as pilots use their competition number as their call signs. Secondly, to easily tell a glider's contest ID when flying in close proximity to one another to alert them of potential dangers. For example, during gatherings of multiple gliders within thermals, One pilot might report 67 Romeo I am right below you. Fiberglass gliders are invariably painted white to reflect sunlight. Since fiberglass resin softens at high temperatures, white is used to reduce overheating from the sun. Color is not used except for a few small bright patches on wingtips. These patches improving a glider's visibility to other aircraft while in flight. Such patches are obligatory for mountain flying in France. Non-fiberglass gliders made of aluminum and wood are not so subject to solar deterioration, and are often quite brightly painted. Comparison of gliders with hang gliders and paragliders. There is sometimes confusion about gliders, hang gliders and paragliders. In particular, paragliders and hang gliders are both foot-launched. The main differences between the types are: competition classes of glider. 8 competition classes of glider have been defined by the FAI. They are: standard class, 15-meter class, 18-meter class, open class, 2-seater class, also known by the German name Doppelsitzer, club class. World Class announced a competition in 1989 for a low-cost glider, which had moderate performance, was easy to assemble and to handle, and was safe for low-hours pilots to fly. The winning design was announced in 1993 as the Warsaw Polytechnic PW5. This allows competitions to be run with only one type of glider. Ultralight class, for gliders with a maximum mass less than 220 kilograms. Major manufacturers of gliders. A large proportion of gliders have been and are still made in Germany, the birthplace of the sport. In Germany there are several manufacturers, but the 3 principal companies are DG Flugzeugbau GmbH, SCHEMPP Herth GmbH, Alexander Schleicher GmbH and Company. Germany also has Dem and Lang Aviation. Elsewhere in the world, there are other manufacturers such as Jonker Sailplanes in South Africa, Sportina, Aviacija in Lithuania, Allstar PZL and PZL Bielsko in Poland, HPH in the Czech Republic and AMS Flight in Slovenia. See also, military glider, list of gliders, history, Paragraph N. Rosettengesellschaft, Schweizer Brothers, gliding as a sport, gliding competition, other unpowered aircraft, rotor kite, unpowered flying toys and models, paper plane, radio-controlled glider. References. External links, information about all types of glider, Sailplane directory, a Euro and enthusiasts website that lists manufacturers and models of gliders, past and present. KANJA ultralight glider, 8 aeronautical engineering students build a glider, Kanja. FAI web pages. FAI records a Euro sporting aviation page with international world soaring records in distances, speeds, routes, and altitude, links to all national gliding federations.